Imagine walking into a supermarket with just one billing counter. The cashier can serve one customer every minute. If only one customer arrives each minute, everything works smoothly. No one has to wait. But what happens if 5 customers arrive every minute? The cashier still serves only one per minute, so the remaining customers start waiting in a queue. As more customers arrive, the queue keeps growing, and everyone waits longer before getting served. This simple scenario sets the stage for understanding why systems slow down, not just in supermarkets, but in many other areas. Supermarket queue isn't just a real-world problem. The same thing happens in computer systems. Imagine your backend server can process 100 requests per second. If users send only 50 requests per second, the server easily keeps up. But if 500 requests per second suddenly arrive, the server cannot process them all immediately. Some requests are processed, while the rest wait in a queue. As the queue grows, users start experiencing higher response times. Eventually, requests may even time out or fail. This mirrors the supermarket scenario, but in the digital world. Notice something interesting. The server didn't suddenly become slower. It still processes requests at the same speed. The slowdown happens because requests spend more time waiting before they are processed. This is a common misconception in software engineering. When users say, the application is slow, the actual processing might take only a few milliseconds. Most of the delay often comes from waiting. Understanding this distinction is crucial for diagnosing performance issues in any system. Queuing theory is the branch of mathematics that helps us understand these waiting times and delays. It answers questions like, why does latency suddenly increase under heavy traffic? How many servers do we need to handle 10,000 users? When should we add more servers? Why does CPU usage of 100% cause huge delays? How can we estimate the capacity of a system before it fails? These questions are essential for anyone managing or designing systems that need to scale efficiently. One of the most noticeable effects of queues is the sudden increase in latency when traffic spikes. For example, if a web server is comfortably handling requests, everything feels fast. But when the number of incoming requests exceeds what the server can process, latency jumps. Users experience delays, and sometimes requests fail altogether. This isn't because the server is broken. It's simply overwhelmed by the volume, and requests are forced to wait their turn. Queuing theory helps us estimate how many servers are needed to handle a certain number of users. For instance, if you expect 10,000 users, you can use mathematical models to predict how many servers will keep response times low and prevent queues from growing too long. This proactive planning is vital for businesses that want to ensure smooth user experiences, especially during peak times or unexpected surges. High CPU usage is often linked to delays in processing requests. When a server's CPU hits 100%, it can't process any more requests at once. This causes queues to grow rapidly, leading to longer wait times and potential failures. Queuing theory helps predict when CPU bottlenecks will occur, allowing engineers to take action before users are affected. Queuing theory isn't just for web servers. It's used in databases, load balancers, message queues like Kafka, and cloud platforms. Anywhere requests or tasks need to be processed, queues can form. Understanding how these queues behave helps engineers design more reliable and efficient systems, whether they're handling financial transactions, streaming media, or managing large-scale cloud infrastructure. Many people believe that when an application is slow, it's because the server itself is processing requests slowly. In reality, most delays come from waiting in queues. The actual processing time is often very fast, but the queue introduces latency. Recognizing this helps teams focus on the real source of performance issues, rather than chasing false leads. As businesses grow, their systems must scale to handle more users and requests. Queuing theory helps predict when and how to scale, ensuring that performance remains high even as demand increases. By understanding the mathematics behind queues, engineers can make smarter decisions about infrastructure investments and avoid costly downtime. In summary, systems slow down not because they process requests slower, but because queues form when demand exceeds capacity. Queuing theory provides the tools to understand, predict, and manage these delays. Whether you're running a supermarket, a web server, or a cloud platform, mastering queues is essential for delivering fast, reliable service. By applying these principles, you can ensure your systems stay responsive and efficient, no matter how much they grow.